In this video, I want to look at the nature of diffusion style transfer laws. And I'm going to start by using an example of heat flow, and specifically heat flow by the process of conduction. And that is to say heat flow without any movement of matter. We're not moving things from one place to another. We're just moving heat by the vibrations of molecules. And the law that we have here is something called Fourier's law, Fourier's law of heat conduction. And it's got a form which all of these laws are going to have that looks like this. I'm going to use J here to represent heat flow. The flow of heat is equal to some constant C, which is called the thermal conductivity or diffusivity, times the quotient of the temperature change divided by the distance over which that temperature change occurs. We call this thing the gradient of temperature. So if I were to graph temperature on the y-axis versus distance on the x-axis, it's essentially the slope of this red line. So there's actually a negative sign here too, I should also mention. That negative sign ensures that heat flow is always going to go from regions that are hot to regions that are cooler. So in this example, the heat flow will be from left to right. And what Fourier's law says is that the heat flow, the amount of heat flow, is proportional to two things. One is this thermal, I'll call it thermal diffusivity or conductivity, call it thermal conductivity, which represents the ease with which heat can flow through a specific material. So certain materials are easier for heat to flow through, like metals. It's easier for heat to flow through a metal than something like styrofoam, right? So the heat flow, the rate of heat flow, depends on the thermal conductivity, which is a property of the medium, times this gradient of temperature. The steeper that gradient, the faster is the heat flow. This figure shows the effect, which you probably already know about or have intuition about, of the thermal conductivity. Remember, this is the thermal conductivity here. And the idea here is that the heat flow from, for example, your hand into which is warm, into this cold beverage is going to be faster through a material like metal that has a high thermal conductivity than it will be through a material like styrofoam here, which has a low thermal conductivity. And so the result is your hand will feel really cold if you're holding a cold can of pop in a metal container, and it won't feel that way if you're holding it in a styrofoam container, because the rate of heat flow from your hand into the liquid is dependent on the thermal conductivity. Again, let me just write the equation down for the third time. The heat flow is proportional to the thermal conductivity times the gradient in the temperature. So temperature is the driver for heat flow. And the temperature gradient is essentially the slope of that red line. So when the red line has a steeper slope here I have the same temperature difference over a shorter distance, and with the result that the slope is steeper, then I would expect faster heat flow than what I showed you in the first slide. In contrast, if I have a more gentle slope here, then I would expect more slower heat flow across whatever that distance is. And in the extreme, if there is no temperature difference between one side and the other side, if the drink inside the container is exactly at the same temperature as your hand, 98.6 presumably, then there will be no heat flow in either direction. So again, the idea is that the heat flow is equal to the product of this property of the medium called the thermal conductivity, times the gradient in temperature. So temperature is the driver for heat flow. But this exact form of this equation actually appears in all sorts of other transfer expressions. For example, if we're thinking about the flow of matter via the process of diffusion, that is the movement, for example, of water vapor molecules from high concentration to low concentration, this also follows a law of diffusion. This, in fact, is called Fick's law of diffusion. And it's exactly the same law. J now represents the flow of matter, the flux of matter, and that is proportional to something called the diffusion coefficient, which is just, let me just write it out here. It simply plays the same role as the thermal conductivity. A high diffusion coefficient means the material allows mass to diffuse through it easily. A low diffusion coefficient means it makes it hard for mass to diffuse, times the gradient in this case of concentration. So it's the change in concentration with respect to distance. Concentration is the driver of mass flow. Same exact equation. The same equation appears in the study of electricity. So in this case, J represents the flow of current, and it is equal to the product of a property of the medium called the electrical conductivity. Electrical conductivity. Sometimes you may also see it related to something, the reciprocal of it, which is the electrical resistivity. Times, in this case, the gradient of voltage, change in voltage with respect to position. This is Ohm's law of current flow. And what actually happens in the flow of electricity is we always just lump these two terms together to form the electrical resistance to get Ohm's law. But it's basically exactly the same law. The flux of current is equal to the product of a constant, which depends on the kind of material. Certain materials are better electrical conductors than others, times the gradient in voltage. Finally, the same exact equation appears, the same form of an equation appears in the study of groundwater, where J now represents the flow of groundwater, something called the specific discharge, and that can be expressed as a product of the hydraulic conductivity, which represents the ease with which groundwater can flow through the pores of a medium, times a gradient of a variable called hydraulic head, which is something we'll learn about later when we study groundwater. But it's exactly, this is X, exactly the same idea. So if this slope is the slope of change in head, H is the variable for head, divided by change in distance, the rate of groundwater flow is proportional to the steepness of this slope. When the slope is 0, there is no groundwater flow. When the slope is steep, groundwater flow is faster. When the slope is gentle, groundwater flow is more slow. And it also depends on a property of the medium, which describes how easily in general water can flow through that medium, called the hydraulic conductivity. So we have actually have 4 of these expressions, all which have the same form, and they are very, very common in hydrology and in other fields, and you should basically know how they work. So what we have is some kind of flux of some kind of substance, some kind of heat or mass or voltage, or I'm sorry, current, and it's going to be proportional to some property of the medium that describes how easily that stuff can flow through the medium, times the gradient of some variable. I'll just call it X for now. That X can stand for lots of different things, but it's a gradient. It's the change in, oops, that was probably a bad choice. Let's call it the change in S for stuff with respect to X. So S might be temperature to drive heat. S might be head to drive groundwater flow. S might be voltage to drive current, or S might be concentration to drive mass. But it's all the same formula with just different variables for J and C and S.